if we connect the positive terminal of the battery with the p-type semiconductor region, and the negative terminal is connected in this fashion with the n region of semiconductor, we have a forward bias junction. By forward bias, it means that there will be a diffusion of majority carriers from one region to another region in which they become minority carriers. And why it happens is because the net E field decreases. Okay, the E field, due to the applied bias, external bias VD, tends to decrease the overall field which is directed from N to P type region. Okay, because you see what's happening over here is that in absence of bias, when there is no VD, it's open circuit. You have a barrier potential due to the uncovering of immobile charged ions on both sides, and they try to halt the diffusion process of holes from P region to N region and electrons from N region to P region, right? And an equilibrium is established, so there is no transfer of charges, right? And that's because of the barrier potential, and that is because of the E field setting up, and that balances out the diffusion, the concentration gradient across the PN junction, right? This is this is what we discussed last time, and but when you apply a forward bias, well, it turns out that you have a diffusion process because the equilibrium is disturbed, a delicate equilibrium is disturbed, and then the holes from the P region they start diffusing due to the concentration gradient, new concentration gradient. They start diffusing from P to N region. Similarly, the electrons, they start flowing across the junction from N region to P region. There is a small diffusion current because of the forward biased bias VD or E field that reduces the net E field directed from N to P region. And because of this disturbance in the equilibrium, there is a small diffusion current. Okay, and then the holes which are majority carriers in the p-type region, they enter into the n-type region of the semiconductor in which they are minority carriers. Okay, so the concentration of the hole increases in the n-type semiconductor region, and well, what happens then is that you have some recombination with the majority carriers. So in equilibrium state, the concentration of these excess hole, which are the minority carriers, they decreases. Okay, so they decrease, and this happens, and a similar situation happens on the p-type semiconductor region. So the diffused electrons from N region to P region, okay, which have crossed from N to P region, there's an excess electron concentration which might recombine with some of the holes which are majority, and then the concentration tends to fall and the equilibrium conditions are again maintained. Okay, but this due to the application of VD, as long as a positive VD is applied and such that the positive terminal of the battery is connected to the p-type region and negative of the battery is connected to the n-type region, so you have a forward biased PN junction. As long as VD is there is some diffusion of holes and electron. Okay, now this hole and electron diffusion creates current across the junction, and this current is of the exponential nature. Okay, so over here you see the ID current is due to the applied VD, and that is external bias. VT is the thermal voltage, which is about 2.6 millivolts at room temperature. The parameter N over here is a new factor, which is known as the Ideality Factor or the emission coefficient. So the parameter N is usually called the emission coefficient or the Ideality Factor, and its value is lie between 1 to 2. I mean, what this factor does is it's modeling the effect of recombination of charges in the space charge region or in the depletion region. And if there is more recombination, then there is less current. Okay, so this Ideality Factor increases to at most 2. But if there is less recombination, there's more current, then it's close to 1. Okay, for the sake of simplicity, we can keep it to 1 for now. The other parameter that you look in this expression that you're looking at is this expression is IS. IS is the reverse bias saturation current. Okay, and this ID current, you must remember, is due to the applied external bias. You see, if you don't have an external bias, well, it's minus IS, and IS is a very small, in most cases it's negligible. You see the order of IS, the reverse saturation current, is 10 to the minus 18 to a pico ampere. It's negligible current, okay. It's almost zero, so you don't have any current in the reverse bias. For example, if we plot VD and ID characteristic of a diode, ID being the diffusion current of the charge carried across the PN junction, okay, this is VD at 0. If there is no VD, well, or if VD is less than 0, reverse bias, you have a very small or negligible current, which is equal to IS. So ID over here is minus IS, and IS can be neglected. In most of the cases, it's 0. It's almost 0, right? I mean, this minus sign is because this VD is not there. Okay, so IS is a very small quantity. Okay, or you can, in ideal cases, you can take it to 0. It's only when the application of when you applied VD in this region, which is greater than 0. Okay, for a positive VD, you start having some respectable current across the junction due to the diffusion of carriers, and this could be respectable up to, you see, the order of milliamps. Okay, so up until it reaches the barrier potential, and after the barrier potential, let's say VB, the current is going to rise exponentially. So ideally, the behavior of a diode can be seen as it's a non-linear device. Okay, I mean, the ID and VD characteristics are not, it's not a straight line connecting those two quantities. It's a non-linear junction diode. Okay, so a theoretical relationship exists between the voltage and the current in the PN junction. It's given by this relationship. So forward bias voltage results in a gradient in the minority carrier concentrations, which in turn cause diffusion currents, and this diffusion current due to the applied VD is given as such, where IS is the reverse bias saturation current, it's a small current, and VD is the thermal voltage, and is the combination, and is the emission coefficient of the diode, which for simplicity can be taken as 1, okay, which takes into account the recombination of the charges in the space-free region. So the emission coefficient takes into account any recombination of electrons and holes in the space charge region. Now, at very low current level, the recombination may be a significant factor. Because of a lot of recombination, you don't have a lot of current, so you have low current, and this value can be close to 2, right? Now, at higher current levels, the recombination is less a factor, and the value could be taken as 1. So, unless otherwise stated for this text, we'll assume the emission coefficient or the ideality factor of diode to be equal to 1, and this PN junction with non-linear rectifying characteristics is called a PN junction diode. So this example shows the amount of the current the PN junction diode is going to handle for two different values of VD in forward and reverse bias. So if you consider a PN junction, silicon PN junction at room temperature, saturation current is given as 10 to the minus 14 amps. The ideality factor is set to 1. So you have to determine the magnitude of the current through the diode. So if you plug those values in the diode equation, the diode current equation, N is set to 1, VT is the constant 0.026. You see that with a very small amount of forward bias voltage, VD, we have a respectable milliamps junction current, right? And if the terminals are reverse biased, so the second case, the first case is for the forward bias junction, okay? And VD is greater than 0, it's a small voltage. It's just enough to reach the barrier, just to, eliminate the effect of the barrier, which is halting the process of diffusion of charge carriers across the junction. You see, a respectable current can be obtained from the diode if you increase VD. And if you go on further increasing VD by, let's say, twice or thrice, let's say it's 1.4 volts or 2.1 volts, then even this 1 is not important. You're going to have a very large current. It's an exponential current, right? And it's going to grow exponentially like this. So 1 can be ignored in this equation thereafter. But however, if for a very small VD, if you reverse the potential, so in this case you have a reverse biased junction diode, you can see that the value of the current falls to 10 to the minus 14 amps, which is approximately the reverse saturation current. And you can, in most of the practical cases, you can neglect this. So in the reverse bias where VD is less than 0, you don't have any current. Okay. for VD less than 0, for VD in this region, the diode is reverse biased. Okay, this is reverse biased diode, so you don't have any current. In forward bias, yes, you are, as long as VD is greater than 0, as long as VD is greater than 0, there's going to be a diffusion process of charge carriers, and depending on how far you are away from the barrier potential, you're going to have a very large current, the forward current, okay, forward diode current. So although IS is quite small, the reverse saturation current is small, a relatively small value of forward bias voltage can induce a moderate junction current. Now with a reverse bias voltage applied, the junction current is virtually 0, okay. Now, you see this exponential behavior is shown in the forward bias region, the reverse bias region. This region is for VD is less than 0, and in almost all practical cases, you don't have any current for VD less than 0. ID is minus IS, which is 10 to the power minus 14. Well, it could be, it could reach, for example, picoamps, but it's not important. I mean, there could be, for example, generation of some charges across the space charge region, but even then, it's so small that we can neglect this. Ideally, you can have you can assume zero diode current across the junction when the battery terminals are such that the diode is reverse biased. Okay, in a forward bias region, you can have a significant current which is exponential. So as long as VD is greater than 0, you have a forward bias junction. You can increase your current exponentially. Okay, you can see over here, current is rising exponentially. So figure 1.17 is a plot of a derived current voltage characteristic of a PN junction, and for forward bias voltage, the current is an exponential function of the voltage. Right. There's another figure 1.18 that depicts the forward bias current plotted on logarithm scale, because you see the characteristics are it's an exponential. So if you take the logarithm on both sides, you can have a linear scale, okay, and this is shown in figure 1.18, and this is your logarithm of the current versus the voltage, and this is the ideal IV characteristic of a PN junction diode with current plotted on a log scale. For IS reverse saturation as minus 14 amps, so it starts with 10 to the minus 14 amps, and then it increases. I mean, for 0.6, you can see it goes all the way up to 10 to the power minus 4 amps with ideality factor n equal to 1. So the diode current increases approximately 1 order of magnitude for every 60 millivolt increase in the diode voltage. So it's the same curve, but it's plotted on the logarithmic scale. Okay. So with only a small change in the forward bias voltage, the corresponding forward bias current increases by the orders of magnitude. So for a forward bias VD greater than 0.1, the minus 1 term in the diode current equation can be neglected. So you see, it's such a large current after the barrier potential VBI that you don't even need to consider this term minus 1. It's becoming significant in the forward bias region. So in the reverse bias, the current is almost 0, which can be seen over here. Okay. So figure 1.19 is showing you the 1.19b is the diode symbol. P-type region is shown by this triangular region, which is positive, and the negative is shown by the straight line. So these two figures, they show the basic PN junction diode. This is a simplified geometry in part A, and part B of this is the circuit symbol and the conventional current direction, the voltage polarity. Okay, so if positive of this ID is greater than 0, if the junction is forward biased. Okay, if ID, there is no ID for the reverse bias PN junction diode. So 1.19 shows the diode circuit symbol and the conventional current direction, voltage polarity. However, the diode over here, can be thought of as a voltage control switch. Why it's a voltage control switch? Because as long as VD is there, a positive VD is there, it's going to control the flow of exponential current. Okay, the ID exists. So if you have to turn on the diode, you can think of this as a voltage control switch. You apply the voltage and you have the ID. Okay, that's the forward junction current. But if you want to turn off the device, all you have to do is you have to reverse the potential, you have to reverse the polarities, make it reverse bias, and then there is no current. So it can be thought of as a voltage control switch, and that is off for the reverse bias voltage. So when the switch is off, there is no current, it's open circuit, and it's on for the forward bias. So it's on, the switch is on, or you can say the switch is short circuit whether there is a current. Okay, so it's a short circuit. But in the off state, The diode is open circuit. The diode is open circuit. That means there is no current. Okay. I mean, these are just the angles you can look upon the same device. The point is the device is non-linear. Okay. It has a non-linear Idvd characteristics, and it only conducts in the forward bias region, not in the reverse bias region. Okay. So in the forward bias or in the on state, the relatively large current is produced by a fairly small applied voltage. In the reverse bias, it's off, only a very small current is created. So when the diode is reverse biased by at least 0.1 volt, the diode current ID is minus IS. The current is in the reverse direction and is constant, hence the name is reverse bias saturation current. Now the real diodes, however, exhibit reverse bias currents that are considerably larger than IS. And this additional current, as I've mentioned earlier, is due to the generation current and is due to some electron and holes being generated in the space charge region. But this phenomena of generation of holes and electron generation can be neglected because, I mean, the order is still small. You see, typical value of IS that we are assuming is 10 to the minus 14 amps. But typical value of reverse bias saturation current may be nanoamps or 10 to the minus 9 amperes, which is again negligible. So even though this current is much larger than IS, it is still small and negligible in most cases. So in reverse bias, the diode is open circuit. That is, there is no current. The switch is open, so it doesn't has any conduction of current or the diffusion of charge carriers across the PN junction. Okay, so that's all.